right, not every function has an inverse. Fortunately, there's a really easy test to determine if a function has an inverse. This test will look pretty familiar. It should look a lot like the vertical line test that we did in the very first section, 1.1. Remember, the vertical line test told us if the graph we were looking at is a function. The horizontal line test is going to tell us if the function has an inverse. So here's how it works. A function does not have an inverse if there is a horizontal line that intersects the graph at more than one point. Okay, so in other words, we want that horizontal line to only touch our graph in one place the whole way through. So I'm going to use this ruler to mimic a horizontal line. As I look at this first graph here, as I move my horizontal line, I see that it's only touching my graph in one place. So this first one has an inverse, or it is invertible. The second picture, the one in the middle, as I move my horizontal line, I'm seeing that it's touching my function in more than one place. Right, so this particular horizontal line touches in those two spots. So this middle one is not invertible. And then the last one, so this last one kind of levels out a little bit, but it is still really slowly decreasing. And as we move that ruler along, even that part that starts to look like it's maybe flattening out a little, we're still only touching our graph in one place. So this last one also has an inverse. All right, so now that we've seen a kind of a really simple test to do that, let's talk a little bit more about what this is actually saying and what these two dots here represent. So for a function to have an inverse, each x has to go to a unique y in the range. So I have this function y equals 2x plus 1. You'll notice the -2 goes to this -3, the 0 goes to the 1, the 3 to the 7, the 5 to 11. So none of these numbers in the range get used more than once. This function over here, y is equal to x squared minus 1, what we notice is that when x is -2, y is 3, and when x is +2, y is 3. So I have two different numbers in the domain going to the same place in the range. And so that would mean that there is no inverse for this function on the right-hand side. So we need each thing in the domain, each x value, to be paired to a unique y value. All right, let's take a look at one more example of this. So this is the vending machine problem from the very first weekly review. And on that review, you had to go through and decide which was a function and which was not. So the first one is a function because each number went to one thing. The second one was not a function. And that's because the one could have gone to the M&Ms or the dried fruit. So it goes two different places, and so therefore it's not a function. The third one, the 1 only goes to M&Ms, the 2 only goes to M&Ms. So this works fine. This one is a function. And then I'd love for you to go ahead and pause the video and decide if either 1 or 3 is going to have an inverse based on that information you have. So take a second and think that through. All right, so vending machine 1. So remember our definition here is that everything in the range had to come from a unique x value. So there's no doubling up. When we go through vending machine 1, we see that there's no doubling up of any of these here. Okay, so each of these things in the range is unique. So this one has an inverse. Machine 3 does not have an inverse. And the reason for that is that these things are getting doubled up here. So both the 1 goes to the M&Ms and the 2 goes to the M&Ms. So if you told me you had gotten M&Ms out of the vending machine, I know that you pushed either the first button or the second button, but I don't know which one. And so for that reason, there's no inverse here.